Very good afternoon to all and all. Today we are going to discuss about the fifth unit of design of steel structures, that is a design of steel flexural members or design of flexural members in steel. So why we need to design a flexural members? What is the purpose of designing the flexural member? First one is for economic purpose or economy purpose. Choose the lightest beam that can be carried the load. So we have to select the beam which is having the weight is less but carrying a load is maximum. That is the economy. Second one is serviceability. May need deeper beam to prevent serviceability problems such as deflection or vibrations. This one is bending about a strong axis. Consider the simply supported beam having a uniformly distributed load throughout its length. This is the uniformly distributed load. This is the beam, and this is the support condition. One end is having hinged, another one end is having a roller support. This beam is called a simply supported beam. So you have consider a beam of simply supported beam subjected to uniformly distributed load throughout its length, and the major or a strong bending axis in x-axis and weak bending axis in y-y axis. Uh, and this is the stress strain in cross section or stress strain distribution in cross section. This is the neutral axis. Initially, the beam is having the stress is less than yield stress. Stress is less than yield stress. After that, increasing the moment, the stress is the most distant fiber or bottom fiber will yield the first yielding. After further, we are increasing the stress, increasing the couple moment. The stress is increased both tension and compression zones. Further, we are increasing the inner fiber will be yielding so that the beam will be fully plastified. This is the fully plastic stage stress strain curve. This is LRFD equation. So where load effect is less than or equal to factored resistance. So load effect, which means MU, ultimate moment of resistance, is less than or equal to pi into Mn, where Mn this is the stress strain curve for a cross section compared with the strain. Initially, there is no strain, only stress is directly proportional to the strain. Stress is directly proportional to the strain. Further, we are increasing the load. The internal resisting force will not be occurred, only the strain is increasing. That way, stress is equal to strain in y direction. Finally, the strain hardening stage will occur. After that, it's a complete or fully plastic stage. And this is the specification for flexural members. This is the basic strength in CB. This one is CB equal to 1.00 into basic strength. This is MP, fully plastic moment. In elastic, this is elastic region. This is the plastic region. This one is moment of resistance. This one is fully plastic moment. Here, part 5 design of steel flexural members is given in table 5 to 3, page number 5 to 42 to 5.48. Beam tables, also beam charts also given in table 5.5, page number 5.71 to 5.102. Also beam diagrams also given in steel table, table 5 to 17, page number 5.162 to 5.177. So flexural design example. We are to select the lightest A992 steel beam that can carry a live load of 1.9 kg per feet and a dead load of 1.4 kg per feet for the beam of 33 feet. Assume the first continuous lateral support and then the lateral support 10 feet from the each end only. This is the deflection, how to calculate the deflection. Serviceability is not called as strength, so it is not a strength. Calculated for service load only KBC. So del maximum, deflection maximum equal to L divided by 360 for floor members. Also, we can take the value of maximum deflection equal to L divided by 240 for roof members, where del maximum equal to maximum deflection, L equal to length of the beam or span length. And next, deflections, del equal to ml square divided by C1 Ix can also be written as del divided by L equal to ml divided by 12 C1 Ix. Okay, check deflections of beam chosen in the previous examples. This is for beam shear. We have to calculate the maximum bending moment in simply supported beam having a uniformly distributed load throughout its length. The maximum deflection of the simply supported beam equal to WL squared 8. This equation is derived by determining the reactions initially by using the equilibrium condition summation of W equal to 0. After getting the reactions, if the reactions will be WL by 2 and RA equal to WL by 2, also RB equal to WL by 2. After that, you can take the moment at support at midpoint. Then only you can get the value WL squared by 8. If you finding the moment at the supports, support A and B, you can get the values of 0, 0. At support A also maximum minimum 0, and support B also maximum minimum is 0. Also, the internal shear of the beam section is WL by 2. This one is beam shear. How the beam is getting shear. Stiffeners, to avoid the shearing of beam section, we have to provide the stiffeners. This is stiffeners. And this is how to check the shear strength of the beam. Pi B Bn equal to 0.9 into 0.6 into FyWAW. If H divided by thickness of the web is less than or equal to 2.45 into root of E divided by Fy. True, this is true for steel shapes, where Fyw equal to yield strength of the web. Fy for steel shape, Aw equal to area of the web. The area of the web can also be determined D into Tw. This is the construction details. This is the section of the beam. This one is floor beam joints. Here, peel and support bond. This one is girder. Also, the plan view is given and section view is also given. This is the plan of the building, and here the sectional view of the beam is given. KBC minimum distributed live loads are also given in this table. This is composite construction, details of shear connectors. In composite construction, a C composite equal to 0.85 FCBA, where T equal to Fy into AS, C equal to T cannot be exceed force carried by studs, summation of Qn. Summation of Qn equal to 0.85 FCBA, where A equal to summation of Qn divided by 0.85 FC dash into B. Composite construction, Y1 equal to distance from PNA to beam top flange, Y2 equal to distance from concrete flange force to beam top flange, B equal to effective width of the concrete slab flange, A equal to effective concrete flange thickness. These are all the procedures how to design the structural member and why we need to design. What are the purpose of designing the structural members also. Now we are going to discuss concrete flexural members. This is the reinforced concrete flexure members. Already we discussed the steel reinforced flexure members. In our syllabus also, we are studying the design of steel structural elements. So you have to know all the design steps for steel structural elements or flexural members made up of steel. So you have to know this, but you don't need to know very much about this one because you already learned in design of reinforced concrete structures. So the design criteria for concrete flexural members is serviceability, cracks with limits, deflection limits, strength must provide adequate strength for all possible loads also. Thank you.